day, I came across a video on the Machine Learning Street Talk channel called Neural Nets Are Elastic Origami. It's an interview with Professor Balestriero. He talked about this super cool geometric way of thinking about neural nets. Basically, just like origami folds a flat sheet into complex shapes, neural nets fold and carve up input space into all these non-linear decision regions. And then grokking came up, the weird thing that the generalization occurs long after achieving near-zero training error. I came from an optimization background, so things like hyperplanes and local complexity, once a real headache for me, now totally draw me in. I figured why not take a break from new papers? Let's visit the grokking paper from a year ago.
Let's talk about what this paper calls grokking. You might have seen this strange effect before. A deep neural network gets near-zero training error, and yet it doesn't generalize at first. We might expect that once a model memorizes its training set, it should perform well on unseen data right away, right? But in grokking, that's not what happens. Instead, the model can spend a long time just overfitting, getting better and better at training examples, but not improving on the test set. And then suddenly, it wakes up and starts generalizing effectively. The paper also introduces something called delayed robustness, which is the idea that networks do a similar thing when it comes to resisting adversarial attacks. They don't just become robust as soon as they learn the training data. Instead, they take extra time, often many training steps, before they start handling adversarial examples well. Look at figure 1 here. It shows a residual network, or ResNet, trained on the CIFAR10 dataset. Early in training, even tiny adversarial tweaks can fool the model. Then, after around 100,000 training steps, the model suddenly becomes much more robust. Another part of this figure tracks something called local complexity, which measures how twisty and intricate the decision boundaries of the network are. Early on, these boundaries are quite messy and jumpy. Later, they smooth out overall, except near the actual decision boundary, where the model stays sharp and focused. The main message is that deep neural nets don't learn everything at once. First, they memorize. Then, over time, they restructure their internal boundaries so that they not only fit the training data, but also generalize and become robust. This restructuring is called region migration and is a central theme in understanding why networks grok. How about an even clearer example of delayed robustness? Check out figure 2, where the authors train a neural network on MLST data. At the start, a small adversarial perturbation completely confuses the model. But then, after about 10,000 steps, the model's performance against adversarial examples suddenly improves. That improvement happens right alongside noticeable changes in its decision boundaries. The paper again tracks local complexity here, showing how it fluctuates during training. There's a characteristic double descent pattern. Complexity rises, dips, then rises again. And when that final rise happens, the model gets dramatically better at handling adversarial examples. So what's causing this sudden resilience? Everybody's from. If you look closely at how the model arranges its decision boundaries, you see that the most nonlinear complex parts are no longer scattered everywhere in it. Instead, they've migrated near the boundaries between classes. The region around each training sample becomes smoother, while the complicated, high-curvature regions gather exactly where the network has to separate different classes. The authors call this region migration, and they find that it's not a one-off quirk. It shows up in different models and datasets. They also test whether there's a particular set of samples that the network groks first by stepping up the intensity of adversarial attacks and tracking which parts of the input space get robust sooner. Interestingly, they find that standard neural nets, even without extra regularizations like weight decay, will eventually grok adversarial examples, but they do so on a much slower timeline than they grok clean data. Now let's focus on local complexity, which is a key concept the authors introduce to measure how much effort the network is putting into different parts of the input space. Look at figure 3. On the left, you see a toy neural net that's partitioning space haphazardly. On the right, there's a learned function that's smoother in some regions and more complex in others. Here's the intuition. The more curved or irregular a function is in a neighborhood of the input space, the more non-linear the model's behavior is there. High local complexity means lots of twisting and turning. Low local complexity means it's relatively flat. During training, the network doesn't just memorize, it reallocates that complexity. Early on, the model might use lots of non-linear boundaries everywhere, but over time, it decides to calm those boundaries down around the training data and move the wild, high-complexity regions to where they matter most, around the decision edges. The paper also ties this to affine spline operators. Basically, Each layer in a deep neural net can be seen as slicing the space into linear pieces. As training continues, these slices aren't static, they get reshaped. That's why we see delayed generalization and robustness. The system is busy reorganizing these slices so that the final boundaries are sharper and more robust to perturbations. This helps explain the weird wake-up effect. The network has already memorized the data, but it's still busy fine-tuning how, exactly, the data is separated in the latent space. It's that reorganization, which takes time, that eventually leads to better generalization. So how exactly do we measure local complexity in practice? Check out Figure 4. Suppose we pick a point in the input space and define a small neighborhood around it, and we see. Then we see whether certain neurons or activations flip within that neighborhood. If a neuron's activation changes a lot, that region is more nonlinear. Another visualization in Figure 4 shows how small neighborhoods get deformed as they pass through layers of a CNN. Early layers might nudge or stretch the neighborhoods a bit, but deeper layers seriously twist them, especially for bigger neighborhoods. This indicates that deeper layers focus complexity differently, and tracking these distortions lets us quantify where the model is thinking harder. In short, local complexity isn't a uniform property of the network. Certain pockets of the input space might be easy to classify, so the network keeps them simple. Other pockets are trickier, and that's where the complicated boundaries end up. Over the course of training, the network shifts complexity away from the simpler areas and intensifies it near the class boundaries. That's another way of looking at why generalization doesn't show up right after memorization, because the network's still in the middle of reorganizing itself into this final pattern. The paper makes the case that grokking isn't just tied to a specific dataset or model, it's actually widespread. Look at Figure 5. Where the authors compare different architectures, like CNNs, and different datasets, like CIFAR10 and CIFAR100. In each scenario, you see the same overall story. The networks first memorize, then, much later, they start to become robust against adversarial examples. Local complexity also follows that double descent pattern. It starts off one way, changes dramatically around the time of perfect interpolation, then shifts again. That final shift corresponds to the point where the network gains robustness. And if you check out the ResNet trained on Imagenette, which is a smaller subset of Imagenette, you'll see the same phenomenon, except the complexity begins at a really high level. The authors formally define how they measure local complexity by counting how many neuron boundaries cut through a region of space. More boundaries mean more complexity. So when a network groks, it's not just memorizing your training set, it's also moving these boundaries around so that complexity is most concentrated in the decision zone. After all, there's no need for complicated boundaries in places where the classification is easy. All of this highlights the importance of that final phase of training, beyond simple memorization, when the network's internal geometry and complexity distribution get rearranged for better performance. What about other architectures like transformers or LLMs? Yep, they grok too. In Figure 6, you can see how transformers go through a very similar reorganization. Early on, the decision boundaries are a tangled mess. Then, as training advances, those boundaries sharpen up, and the wild nonlinear bits relocate to regions where the model is uncertain. Even in networks that use activation functions, like Gaussian error linear units, GILU, the same pattern of region migration appears. The paper even shows a generative pre-trained transformer or GPT model, trained on Shakespeare text, displaying delayed robustness. Test accuracy might stabilize, but adversarial robustness keeps improving long after. That indicates grokking isn't just about vision tasks or small models. The same training dynamic, delayed emergence of robust, well-organized decision boundaries, appears across different tasks and architectures. The takeaway is that grokking is a fundamental pattern, not a curiosity restricted to small demos. If we understand how and why these networks reorganize themselves, we might find ways to encourage it earlier or more reliably. The paper breaks down 3 major phases in how local complexity evolves during training. First, there's the initial descent phase. Right after training starts, complexity can briefly go down, depending on your network's initialization strategy. If your initialization is scaled differently, maybe you skip this phase entirely. Then comes the ascent phase. Complexity rises in the regions around both training and test data. This happens in all sorts of networks, and it keeps climbing until the model fully memorizes the training set. At that point, the complexity near training samples is higher than it is near test samples. The third phase is the star of the show. The paper calls it region migration. Once the model has memorized everything, It starts shifting complexity away from the training points and pushing it toward the decision boundary itself. Visualize it like the network is dusting off the areas around the training examples so they become smooth and easy to classify. Meanwhile, it's piling all the complexity where classification is genuinely hard, right at the edges between classes. If you look at the figures in this section, you'll see how local complexity maps vary across different layers or even in transformer embeddings. Before grokking, it's a big, messy swirl. After grokking, it's organized so that the nonlinear hotspots cluster around the boundary. That's the underlying mechanism that helps these networks jump from memorization to robust generalization. Now, what training details can speed up or slow down grokking? Let's check out Figure 8. One surprising finding is that batch normalization can actually prevent grokking. Why? Because batch norm continually reshapes activations in a way that disrupts the slow, natural reorganization of complexity that leads to delayed robustness. When batch norm is on, the model doesn't get stuck in that drawn-out memorization phase, so it never really goes through the big shift in its decision boundaries. Another factor is dataset size. If you throw a huge dataset at your model, it has a lot more to memorize before it can start focusing on region migration. So with more data, the delayed robustness might show up later or might look different. And how about network width? The experiments show that wider networks actually grok faster. Because they have more capacity, they can learn the training data sooner, which means they can move on to the region migration phase and start cleaning up their decision boundaries. Overall, this tells us that the architecture and training setup can either reinforce or interfere with the model's natural tendency to grok. Things like batch norm might short-circuit it, while increased capacity might accelerate it. Finally, we arrive at a big question. How can we encourage or discourage grokking? Look at Table 1 here, which summarizes a bunch of experiments. Scaling up your model by making it deeper or wider tends to bring grokking sooner. But if you keep piling on more and more data, you stretch out that initial memorization phase, delaying grokking. Batch norm stands out as a special case. Unlike weight decay, which just slows grokking down, batch norm can shut it down entirely. Why? Because it forces the network to maintain certain activation distributions, preventing that slow, large-scale reorganization that we've been calling region migration. Why does this matter? The authors suggest that grokking is closely tied to how networks move their decision boundaries around as they refine their internal representation of the data. The phenomenon hints at deeper connections to mechanistic interpretability, how these models restructure and simplify their decision functions over long training runs. So, if you're after grokking, consider bigger models and be cautious about normalizing layers that might interfere with the process. And keep in mind that grokking seems to follow a memorize first, then migrate complexity roadmap. It's not just about training longer, it's about letting these hidden reorganizations happen naturally. To sum up, bigger models grok sooner. More data slows it. Batch norm kills it. If you're still waiting for your model to grok, just remember, even neural networks need a little time to get it. Maybe they're not so different from us after all. Except, they don't need coffee breaks. So here's to grokking, the art of finally figuring it out after a really long training session.